One of the operating system's key responsibilities is managing processes' access to the computer's shared hardware resources, with memory being a critical aspect. Memory holds the data essential for processes to operate effectively. At its core, memory is a collection of binary data, zeros and ones. Small groups of these bits can represent simple data like numbers, while larger groups can encode complex data such as images or videos. Since memory is a finite resource, there is a limit to how many files and data we can store. This constraint necessitates managing memory efficiently to accommodate as many processes and files as possible while ensuring that access to memory is both safe and secure. Memory comes in different types and speeds, similar to how items are organized in a grocery store. Fast access memory is like items near the checkout counter, quick to reach but limited in size. In contrast, larger storage areas, which are slower to access, are like bulkier items stored farther away. The operating system must manage which data resides in which part of memory and when, optimizing performance and resource use. Next, we will explore how the operating system performs its role in memory management. The term memory encompasses a range of storage types that differ primarily in size and speed. Generally, faster memory types have less capacity, while slower ones offer more space. Registers are the closest to the processor and the fastest type of memory. However, they store the least amount of information. Registers hold the values that the processor is currently using for calculations. For example, when executing x equals x plus 1, the processor retrieves the value of x from memory, loads it into a register, performs the addition, and then stores the result. Cache memory acts as an intermediary between the processor and main memory, RAM. It stores frequently accessed data to speed up processing by preventing delays from repeatedly fetching data from slower memory. Computers typically have multiple cache levels, with each level differing in size and speed. Main memory, RAM, is larger and slower compared to cache memory. It holds the data and instructions that the processor is actively working with. Main memory is volatile, meaning it only retains information while the computer is powered on. Disk storage represents the slowest but largest form of memory. It is used for long-term storage of data, akin to a box stored in a closet. Retrieving data from disk involves more time and effort compared to accessing data from faster memory types. Continuous allocation is a memory management method where memory is allocated in contiguous blocks. This approach requires that a process or file be stored in a single, uninterrupted section of memory. In continuous allocation, memory is allocated in one large, continuous block rather than being fragmented into smaller, scattered parts. Processes or files must fit into this allocated space without being split. This means that a single allocation cannot be used by multiple processes or files simultaneously unless they are all contiguous. Memory fragmentation can occur, where free memory is divided into small, non-contiguous segments, making it difficult to allocate large blocks of memory even if the total free memory is sufficient. Continuous allocation, also known as non-contiguous allocation, is a memory management approach where memory is allocated in separate, non-adjacent blocks rather than in a single contiguous section. This method is used to overcome the limitations of continuous allocation, particularly in systems prone to fragmentation. In discontinuous allocation, Memory is allocated in multiple, scattered blocks, which may not be next to each other. This allows for more flexible use of available memory. Fragmentation is managed more effectively compared to continuous allocation because the system can allocate free blocks wherever they are available, reducing the impact of external fragmentation. Paging and segmentation are common techniques used. Paging is a memory management technique that divides memory into fixed-size blocks called pages. When a program or process needs memory, the operating system allocates these pages to the program in a non-contiguous manner. This method allows for efficient and flexible memory use by managing the allocation of physical memory in smaller, manageable units. Key concepts of paging. Pages and frames. Page, a fixed-size block of logical memory. Frame, a fixed-size block of physical memory, RAM, that corresponds to a page. Page table. Definition, a data structure used by the operating system to keep track of the mapping between logical addresses, pages, and physical addresses, frames. Function, converts logical addresses generated by a program into physical addresses where the data is stored in RAM. Benefits of paging. Eliminates external fragmentation. Since pages can be allocated anywhere in physical memory, the problem of contiguous memory allocation is mitigated. Efficient memory use. Allows processes to use physical memory more flexibly by filling gaps in memory with pages. Paging process. Allocation. When a program requires memory, pages are allocated to it from any available frames in physical memory. Address translation. The operating system uses the page table to map the logical addresses used by the program to physical addresses in RAM. Segmentation is a memory management technique that divides a program's memory into variable-sized segments based on logical divisions. Each segment represents a distinct logical unit of the program, such as code, data, or stack segments. Unlike paging, where memory is allocated in fixed-size blocks, segmentation allocates memory in varying sizes according to the needs of each segment. Key concepts of segmentation. Segments. Definition: variable-sized blocks of memory, each representing a logical unit of a program. Examples include code segments, data segments, and stack segments. Characteristics: each segment has its own base address and length, allowing for different sizes and contents. Segment table. Definition: a data structure used by the operating system to manage segments. It contains information about each segment, including its base address and length. Function: maps logical segment addresses to physical memory locations. Benefits of segmentation. Logical organization. Supports the logical division of a program into meaningful units, improving modularity and management. Dynamic allocation. Allocates memory based on segment size, which can be more efficient for processes with varying memory needs. Segmentation process. Allocation. Memory is allocated to segments based on their size and the program's requirements. Segments are stored in non-contiguous blocks of physical memory. Address translation. The segment table is used to convert logical segment addresses into physical addresses in RAM.